thank you so much for the invitation and for the introduction. And I'm excited to share some of the things that I have worked on related to unusual behavior by crystals that are modulated by fluid physics. So my lab works at the intersection between interfacial phenomena, fluid physics, soft matter, and water chemistry and environmental engineering. And the reason I work here is because there are a lot of interfacial phenomena that are limiting factors for environmental problems. So, for example, fouling control or resource recovery both involve crystallization or accumulation of stuff at interfaces. So I work on a lot of problems related to these areas, including water treatment. Today, what I'll be telling you about two short stories. One on using superhydrophobic materials to induce self-ejection of salt crystals. And then the other on using superhydrophilic materials, so the opposite extreme, to induce this really interesting self-assembly of crystalline patterns. So why do we care about fouling at interfaces? Well, it affects all industries using water, which is pretty much all physical industries use water in some way or another. So anytime you have water in contact with a surface, it can induce this crystallization or fouling. And it's a very expensive problem, costing about 0.3% of the GDP of industrial nations, especially for energy generation or any type of process involving heat transfer. So in my work, we wanted to use drops on surfaces as kind of a macroscopic probe of what is happening on the microscale at those surfaces. Because by monitoring the drop motion and that contact angle movement, you can learn something about what's happening on the microscale, even though you couldn't see it optically, perhaps. So in these experiments that I'm about to present, we took salt water, kind of as a stand-in for maybe ocean water or high salinity brine, placed it on a superhydrophobic nanoscale surface. So this little SEM image in the corner shows the structure of that nanoscale surface. So the reason we did this is because we wanted to see whether the nanoscopic length scale of that surface would prevent crystal intrusion into the material. So in these experiments, we take our drop, put it on the hot superhydrophobic surface, and because it's fairly saturated with sodium chloride, the crystals start to form pretty early on in the process at that air-water interface. And you can see they're cubic because it's sodium chloride. So this is what your table salt looks like, really magnified. But something kind of unusual happens partway through the evaporation process. The water actually de-wets from that underlying superhydrophobic surface. And as a result, you start having evaporation and crystallization moving downward towards that hot surface, which then creates the formation of these legs, which we call crystal critters because they both look kind of like little insects, but then they also move kind of like little insects as they grow. So if we zoom into those legs in a little bit more detail, you can kind of pick a point to watch with your eye, and you can see the reflection of the legs on the superhydrophobic surface. But if you pick a point, you can kind of see that really all of the crystals are forming at that interface, right? So the entire thing is being pushed up and off the surface. And then as you start to run out of water and therefore run out of salt, these legs will taper off into little points. And some of them even completely remove themselves from the surface. So that by the time that evaporation is complete, these things are very, very easy to remove from the surface. They'll just roll right away. And so this is a consequence of that nanoscopic texture. So what are we looking at exactly? What are the legs? So it is my hypothesis that they are hollow tubes of salt, and they're growing at points where liquid remains in contact with the texture after that de-wetting point. So prior to evaporation, you can see that there are little points, if you zoom into the surface, where the liquid is intruding into that nanoscale texture. And then as evaporation proceeds, they leave behind these legs, which very, very much look like tubes. And so it's a little hard to see in the still image, but in the movies, you can actually see bubbles moving through these legs as evaporation proceeds, And in this very fortunate SEM image I was able to capture because most of the legs remove themselves from the surface, you can actually see that it does appear to be hollow. And in some cases, there is a small salt stain that is left behind where those legs previously were on the surface. So that gives us an idea of what length scale these legs are, as well as some idea of like how are the diameters for these different materials. But the interesting thing is, despite these salt stains, which you can see are very, very, very small, they will continue to grow and self-eject on that same area of the surface multiple times. So the hypothesis is that self-ejection occurs primarily because that nanoscopic texture does not allow salt intrusion into the interface. So to test this, we repeated experiments on super hydrophobic microscale surfaces, which have very similar contact angles. So the physics you might imagine would be similar. But what we end up seeing is that we have this Cassie to Wenzel transition where the drop begins suspended on top of those superhydrophobic micropillars, but then falls down with time to form like a donut type structure instead of this crystal critter self-ejected. We repeated the experiment on micro hole surfaces to make sure it's not some type of like a vapor confinement effect in the nanoscale texture. And again, you see that donut shape and that Cassie to Wenzel transition. And then finally, we tested a hierarchical surface, which is a microscale texture that then is overlaid with the nanoscale texture, and again has a very high contact angle. But again, we see the donut formation. So it's really only for the nanoscale texture that you have self-ejection. And so what we think is happening is that when you have a micron scale surface, you allow crystals to intrude. And once crystals start growing either on the sides of those pillars or in between those pillars, you no longer have a super hydrophobic surface. Now you have a material that's a composite contact angle, some hydrophilic crystal regions, some hydrophobic regions of the original texture. And that changes the contact angle, allowing for that crystal intrusion and that Cassie to Wenzel transition. So the micron scale texture allows for this to occur. Whereas on nanotexture, you have confinement effects where crystals trying to grow inside of that small, small region are subject to some amount of pressure due to water structuring around it that then causes them to not want to be there. So we confirm this by taking that deposit from the very last image for the hierarchical surface. We scraped off kind of the macroscopic part of it to see what was happening in between those pillars. And indeed, we find that there are these very, very small salt crystals that have formed in between these 10 micron scale pillars, but you don't see anything for the nanoscale. So that kind of confirms what's happening there. This is also a strong effect of temperature. So if we break up this phenomena into two regimes, one where we are lifting off, and then one where we are growing the legs, what we find is that as we increase temperature, you of course have less overall evaporation time, makes sense because it's hotter, but you also have a shift between these ratios where you spend more of the total amount of time in that growth stage where the legs are growing. So basically the liftoff occurs earlier in the process. And a consequence of this is that when you increase the temperature of the substrate, your legs end up growing faster, and then they also grow to a higher overall height, h. So we can think about using a pretty simple mass-based model on the evaporative flux to think about this. So we know that those legs are hollow tubes, so we can define some outer radius, some inner radius, and then some evaporative flux, JO, at the surface, which is going to be a function of temperature. So we can think about the mass balance for the fluid. So that is just fluid is exiting the tubes at the bottom. So it's just the diameter of the tubes, 2 pi r, multiplied by n, which is going to be the number of legs, and then multiplied by the evaporative flux. And you can do something similar for the crystals, essentially assuming that you're at the saturation concentration so that crystals are constantly forming, and then treating the leg as a hollow cylindrical tube also multiplied by n, the number of legs on a surface. So we combine these and we get some model for the rate of the height of the legs as a function of time. And interestingly, that dependence on n drops out. So it doesn't matter how many legs there are. It's only a function of essentially the evaporation rate, which is set by the temperature, which is indeed what we see experimentally. Sometimes there are 50 legs, sometimes there are like 4. So when we plot this model against the experimental results, we find pretty good agreement where the increase of temperature has this increase associated with the rate of the leg growth using some geometric parameters taken from SEM images. And of course, varying those would kind of shift this line up or down. But overall, the trend is in really good agreement with experimental results. So we can do some fun stuff with this too. Since the legs grow longer and faster on hotter surfaces, if we apply a temperature gradient to the surface, we can actually cause the entire structure to roll. And so this will actually keep happening basically until you run out of water. Those legs will keep growing and self-ejecting. You can actually add another drop of water to this afterwards and let it happen again. So basically what we found is that at high concentrations of sodium chloride, the self-ejection effect can occur. Higher temperature operation is better. It does rely on evaporative flows, meaning that this is not a good solution for bulk anti-fouling, but we have good separation of the water and salts and like very limited crystal adhesion to the substrate. So what is this useful for? One potential application would be in spray cooling of hot surfaces, where we can imagine instead of using fresh water as is normally done, maybe we can use this effect to use salt water instead. But if we want to do that, we need to explore the effect of other contaminants. So far, all of the experiments I've shown have been with pure sodium chloride. But actual waste brines are going to include a lot of other things like surfactants, other types of salts, especially calcium salts, which are known to foul, and then also just good old-fashioned colloidal particles. So the next question was, how do these affect self-ejection? So we'll start with the particles, and this is a very, very high concentration of particles, 2.5%, such that the drop is already cloudy before you even begin evaporating. But interestingly, we find that it does not eliminate self-ejection. You still get this crystal formation and the legs and kind of this full evaporation effect. Similar with sodium chloride, or sorry, SDS, so surfactant, you change the contact angle pretty significantly. It's not even super hydrophobic anymore. But nevertheless, you get this self-ejection effect where now the morphology has actually changed pretty significantly. So instead of a crystal critter, I call these like a mushroom or marshmallow structure. But despite that shift, you still get the self-ejection effect. And once you've removed this from the surface, you can keep doing this multiple times. And so this is at a very high concentration of surfactant, which is pretty interesting because I don't know of any other anti-fouling effect that behaves with surfactant like this. So overall, we found that addition of any type of contaminant did not disrupt self-ejection. And in fact, the opposite was true, especially for the surfactant. Adding a little bit would allow us to have the self-ejection effect even on smooth surfaces, whereas previously we were looking at rough nanoscale surfaces. And this was especially accelerated for high concentrations of the SDS, so 10 millimolar. That's actually above the critical micellar concentration for SDS, so very, very high concentration. And we found the same to be true for the calcium salts as well as for the particles. So more contamination equals more self-ejection, which is a little bit backwards to what you might expect. Essentially, what is happening there is it's because it has to do with crystal legs growing longer and faster when ejection occurs earlier in the evaporation process. And because when you add contaminants, you influence the sodium chloride solubility, crystals start emerging faster. And this is especially true when you have the surfactant. The crystals just start crystallizing right away, which then lets you grow to those longer overall heights. So to conclude this part of the talk, we have found that salt crystals from very high salinity brines can self-eject from these nanostructured superhydrophobic materials, and actually even from just smooth hydrophobic materials in some circumstances. So I'm interested in seeing how this can create opportunities for using waste brine in heat transfer. So now I'm going to shift gears a little bit and talk about semiconductor industry. So clean room fabrication of micro nanostructures is used anytime you have technology, semiconductors, but this produces a lot of hazardous chemical waste every year. So if we can find new ways of creating these materials without producing as much hazardous waste, it would be a very big environmental and economic win. So that brings me to now superhydrophilic surfaces. So it's the same experimental system as actually the first experiments, except now instead of a superhydrophobic, we have superhydrophilic surface, and we've also changed the salt from sodium chloride to calcium sulfate. But we take a drop, put it on a hot surface, and allow it to evaporate. And so this is towards the end of that evaporation as the film completely ruptures. Kind of an interesting thing happens on the inside. We regularly see the emergence of these very nice, well-ordered patterns. And so here's an SEM image zoomed in of one of these patterns. So it's a little bit stochastic, but it's also very highly ordered. And so here's another video of a different example on also a hydrophilic surface. But in this case, the patterns left behind are these sawtooth kind of triangular patterns, which I find very, very interesting. And there was a SEM image showing what these patterns look like. So we can basically predict which regime and which pattern is going to arise just from two parameters, just the contact angle and the temperature alone. And so here we have those different patterns that emerge where on hotter, more hydrophilic substrates, you have sawtooth patterns, and then still hydrophilic, but less hydrophilic, you get those arrays. And so what is happening here is that crystals are leaving behind a record of contact line instabilities, and that different instabilities dominate based on different conditions. So we can look at the overall time of evaporation versus the amount of time that the drop is in that kind of pattern forming, very fast contact line motion regime. And what we find is that the longer that the crystal or the thin film remains pinned by that outer coffee ring of crystals, that will influence that retraction phase, which then basically predicts when these different patterns are going to emerge. So thinner films are associated with the triangles, thicker films associated with those periodic arrays. And so we can also look at high-speed videos to try and understand this a little bit better. So as this contact line moves, you can see that these little beads are pinching off at the contact line, and they kind of get dragged a little bit before they get left behind. And it is little droplets being left behind, right? But then fully evaporates to form those crystals. So it's not that crystallization is happening first, and then the moving contact line just reveals them. It really is that pinch off into those micro droplets that creates the pattern. And this is pretty consistent with a Marangoni-induced instability. The triangles are a little bit more mysterious. So if we do a high-speed video of those formation, you can see that it de-wets. And then the crystal patterns underneath kind of emerge, but they're very different from the arrays, right? It's happening on a much smaller length scale because the height of this film is different. And interestingly, if you kind of zoom in here, you can see that that film is distorted at the location where those triangles are forming. And so what that tells us is that there's a step change in the height that leads to this. And so I'm not going to go into the full details of the physics here because they would take too long, but it is very interesting. And we're hoping to publish some follow-up work on this soon. But essentially what's happening is that there's a step change in that film that then leads to different regimes that leave behind these triangle appearance. So there's a lot of information we can get from looking at the arrays and the different patterns that emerge. So for example, if we look at the
Just to
contact,
let you know,
oh,
Sam, about
yeah,
a few more minutes.
oh,
Yeah,
sure. Yeah.
yeah,
Yep.
yeah.
No worries. We can see that the contact line does not really predict very well what regime you're going to be in, although there is an effect. And the triangles really have a huge amount of different wavelengths they can adapt. And so again, the array regime is very consistent with Marangoni, but the triangular regime have a very different physics involved. So what is this useful for? So at the beginning, I talked about the motivation of cleanroom fabrication, patterning. So how you would normally make these surfaces, so like the micropillar surfaces, for example, I used the first part of the talk, you put on photoresist, expose the pattern, develop it, use reactive ion etch, and then my least favorite part, using hot acid to remove the photoresist. If we can instead use water and calcium sulfate to pattern, you get rid of the photoresist, the developer, and instead of hot acid, you can use water to remove the mask. So we tried this out. We took those crystal patterns, put them in a plasma clean, or sorry, an reactive ion etch to create these pillars. We removed the salt mask with salt water, and we left behind with something that is not perfect, but a pretty good micropillar surface that could be used for superhydrophobic materials. And we did the same with gold sputter coating to create a surface of different patterned regions of gold versus silica. So not perfect, obviously. A mask gives you much better process, much better controllability. But depending on what your needs are, this process can potentially be used to significantly reduce chemical waste. So that is all I wanted to share. I would like to thank my collaborators and mentors. A lot of this work was done during my time at MIT with Kripa Varanasi, and I'm happy to take any questions.